let's get straight into it. Using a rope that will snap if the tension in it exceeds 387 newtons. Let's highlight that. You need to lower a bundle of old roofing material weighing 449 newtons from a point 6.1 meters above the ground. So we kind of see that over here. Obviously, if you hang the bundle on the rope, it will snap because the limit of the rope is you cannot exceed this, it'll snap. So how do we lower it? So you allow the bundle to accelerate downwards. So they're saying if it's falling downwards, the force on the rope or the tension in the rope is lesser because some of the force is contributing to the acceleration. So if it's falling and accelerating, it'll be lesser. And that kind of makes sense, right? So they're asking what is the magnitude of the bundle's acceleration that will put the rope on the verge of snapping. So what is the slowest you can bring this down? What is the minimum acceleration that this needs to have where the rope can still sustain it without breaking? So assuming it's a very consistent 387 and you go to 388, it'll break. So we'll use that force. All right, so let's begin. So we realize that there are multiple forces acting on it, which is the box itself. This roofing, this load has a weight, which is acting downwards, which is equal to 449 newtons. And at max, this rope, which is barely visible, can support a weight of 387 newtons. So the net resultant force acting on this object, F net, is the sum of these two forces acting on it, right? Because these are the only two forces acting on it. So it's the force because of the weight. We're taking downwards as positive. I think it'll help. And the force, the tension in the, I'll just call it T, the tension in the rope that's supporting it, right? So the weight is 449 and the tension is 387. So not much force resolution over here. It's straightforward and we can figure this out just by putting it in the calculator, and it's not too hard. We're getting 62 newtons. So that's the net resultant force acting on this bundle. Now I need to find out the acceleration for this mass. If it's undergoing this much force, I don't know its mass per se, but I know its weight. So I can figure out the mass very easily. So let's just skip to the acceleration. So the weight can easily be figured out, or sorry, the mass can easily be figured out if we use the weight of the object, divide that by just the acceleration due to gravity. And we see that that's very easy. Put in the values, 9.81, 449, that's in the question. We get this. We can use this mass to find out the acceleration. And the acceleration comes out to 1.35. How did I do that? Again, I figured out the mass, I put it in here, and force I knew, right, which is 62, and the acceleration is, sorry, the mass is 49.77, and the acceleration comes out to be 1.35 meter per second squared. Easy. So part A is done. This is the answer to part A. We're done. Easy. The second part, if we go back, which we won't, but if we did, we'll see that they're asking what is the maximum speed when it falls? The maximum speed. So we have an idea of its acceleration, a very good idea actually, the exact idea, and we know the distance. So, you know, what equation tells you about distance and acceleration without the use of time, because no one's talking about time. I think the equation is very straightforward. Let's do that. Okay, so the equation of choice right now is going to be v squared equals to u squared plus 2as. Why I'm using this one, even though I don't like it too much, is because there's no time. Another factor is u squared is actually equal to 0. There's no initial velocity because it's 0. So cancel that out. So it's just going to be, v squared equals to 2as, right? And we're just square root both sides, so we have v equals to the square root of 2as. Putting in the values, we have 1.35 as acceleration and 6.1 as the total distance. Very straightforward. We'll get our velocity as 4.06 meter per second. And that's the speed and answer for question